Today, we are going to review how position, velocity, and acceleration functions are related, and how they appear in calculus problems. These are the key ideas you need to understand in order to solve problems about motion in the calculus unit. This graph shows the position of an object moving along a straight line. The x-axis represents time, and the y-axis represents position, measured from the origin at 0. The time interval shown is from 0 to 8, and the time units are omitted. On the left, the graph is enlarged around time 0 to show the starting value. On the right, the graph is enlarged around the main area we will focus on. The red curve represents the position function, s of t. The blue curve is the derivative of s of t, which is the velocity function, v of t. Finally, the black curve is the second derivative of s of t, or equivalently, the derivative of v of t, which is the acceleration function, a of t. First, let's think about the position function. It shows exactly where the object is at any given time. In other words, the y value itself represents the position. Since the object is moving along a straight line, the graph indicates its location on the line with respect to 0. For example, if this were a quadratic function describing the vertical motion of a ball thrown straight upward from a height of 2 meters, then the y values would represent the ball's height. In this case, for any height greater than 2 and less than the maximum height, there would be 2 different times corresponding to the same height. Ultimately, we must always interpret the position function graph in the context of the problem. If the situation describes a shell fired from a cannon, then the curve represents the height of the shell above the ground. Now, let's return to the original function. Although the object is moving on a straight line, it moves back and forth, so its position is expressed by a fourth-degree polynomial. The first things we need to check are the starting point, the maximum and minimum values, the inflection points, and the points where the graph crosses the x-axis. The starting point of the position function, or the initial position, is found at time 0. Looking at the graph, when time is 0, the position is 8. This means that at the moment we began measuring, the object was located at position 8. Looking at the blue velocity function, at that same time, the velocity is about -14. From this, we can conclude that the measurement did not start when the object was at rest, but rather while it was already in motion. Now, let's look at the local maximum and minimum values of the position function. There are 3 such values. These 3 points represent the moments when the direction of motion changes. For the direction to change, the velocity must become 0. In other words, at those times, the derivative of the position function, which is the velocity function, is 0. So, the maximum or minimum values of s of t correspond to the derivative being 0, which means velocity equals 0, which in turn means the object changes direction. For example, if this were the path of a shell fired from a cannon, then a maximum value of the position function would represent the highest point the shell reaches above the ground, and from that moment, the shell's height would begin to decrease toward the ground. Next, let's consider the inflection points of the position function. An inflection point is something we will study in more detail later, but in simple terms, it is the point where the graph changes from concave up to concave down, or from concave down to concave up. For the position function, an inflection point corresponds to a maximum or minimum value of the velocity function. and it also corresponds to the point where the acceleration function equals 0. In other words, it is the moment when the direction of acceleration changes. Finally, let's connect these ideas to the kinds of problems that appear on exams. Typical questions include: how many times does the direction of motion change during a given time interval? At what moments does the object come to rest? At what moments does the direction of motion change? Over which intervals is the velocity increasing? What is the total distance traveled? And what is the maximum height? All of these can be solved by carefully interpreting the graphs. In the differentiation unit, the position function is usually given, and you're asked to find the velocity or acceleration function by differentiating and then use those to answer the questions. When you move on to the integration unit, the style is reversed. You might be given the velocity or acceleration function, and then you must integrate to find the position function in order to solve the problem.